I'm going to define the coordinate systems for the robot, just like I defined the coordinate systems for the field. So we have a square robot. That's this perfect square, as you can see. Beautiful. And we do have a front of the robot, which we decided was the intake. The robot does need a front in code, even if it doesn't have a front in real life. And we chose the intake as being forward. We also decided that, let's see here. Oh, there's arrows. That forward on the robot is the X direction, and side and left, right on the robot is the Y direction. And positive angle is this way. So that way is positive theta angle. So that is counterclockwise. So this wasn't completely arbitrary. Having X be the forward position for something that's moving is it's not necessarily a standard in I don't know how we call it a standard, but typically people define the X direction as the moving forward direction in a lot of engineering problems, whether it's in robotics or in my field in additive manufacturing. X is the direction that the laser moves. That's sort of a standard that a lot of people use. I don't know there's an official standard written down anywhere for that. You then have Y 90 degrees opposed to that. And then positive theta angle is defined for you. So positive theta should always be counterclockwise. And that is a math standard that pretty much everyone uses. The next sort of thing that we need to talk about is how do we number our Swerve modules? So we've got 4 Swerve modules. Does Alex, who knew this was coming, want to remind us which Swerve module is which?
So I know 0 is in the right top corner, and I know 2 is in the left back corner. But now here's where I mix it up every time. I don't know. I think 3 is in the right back corner, but I always get it wrong, and I don't know which one I'm thinking of whichever way.
You are correct. So 0 is in the front right corner. And then just like we move counterclockwise for the positive theta, we also move counterclockwise for the numbering. So we go 0, 1, 2, 3, counterclockwise around the robot. Does anyone have any questions on the Swerve drive numbering or the coordinate system that we've got? Okay. So before we go any further with the code, we have to talk a little bit about hardware. And Amelie is about to have an aneurysm, but that's okay. So the reason that we have to talk about the hardware for this is A, we've got a lot of sensors that we need to work with. And B, we're asking the robot to do some pretty crazy things. And so there are going to be physical limitations with what the robot can physically do that we have to take into account with our code. And so a lot of code does sort of depend on that. So each Swerve module has 2 motors. It's got the motor that drives the wheel, which we call the drive motor. It's got the motor that changes the module angle, and we call that the Azimuth motor. I did not make up the word azimuth just to be annoying. Azimuth is a fairly standard term for describing something that rotates in that particular plane. You see it a lot with Swerve drives, you see it in astronomy, you see it in a couple other places. So not made up just for funsies. You then have several encoders. You've got, so each of the motors that we're using is a NEO right now. And whether we use a NEO or a Falcon in the future, they're going to have integrated encoders. So there's an integrated encoder on the drive motor, and there's an integrated encoder on the Azimuth motor. And then we have another encoder, which I'll call the, right now I'll call it the, it's the, we'll call it extra encoder on that Azimuth motor. Does someone want to talk about or guess as to why we've got an extra encoder on the Azimuth motor? How about we hear from the designer of the Swerve drive? I'm so sorry. I think Adam would be actually happier if there wasn't an extra encoder on the Swerve drive. We also need to get Adam a mic at some point so he doesn't have to type everything out. Okay, so Adam says, so the extra encoder is a 1-to-1 ratio with the angle of the module. So the encoder reads the angle of the module so that the robot doesn't have to do math to see what the angle of the module is, which can be a problem if the robot browns out. So yes, so what Adam's saying is that for every 360 degrees that the azimuth motor spins, or that the wheel module spins, the extra encoder will also spin exactly 360 degrees. So 1 degree on the azimuth, on the module azimuth angle is always going to be exactly equal to 1 degree on this extra encoder, and it's designed that way. The reason that we've done this is twofold. So, well, I don't know if I'd say twofold. The reason that we've done this is, yeah, I guess twofold is fair. So, if the number of, if say the encoder rotated only 180 degrees every time the module rotated 360 degrees. So if we had, let's see if I can draw here. This is going to be a very bad circle, so I apologize. If the module rotated 180 degrees, and then this is the module, and then the encoder rotated 360 degrees, we would have a bit of a problem. Now, you wouldn't be able to independently know whether the robot was, whether the robot's angle on, the angle of the module was here or here. because it could be, oh, sorry, undo that here. So you want to know whether the module is located there or there at any point in this process, because the value on the encoder would be the same for these two different locations, angular locations on the wheel. Now, this isn't an unsolvable problem. You could notice in the code that as you spun from 0 to 360, you could say, okay, this is the first time I've gone from 0 to 360. And then when you start going from 0 to 360 again, you say, okay, this is the second time I've gone from 0 to 360. And you could count, you know, which number of the 0 to 360s you've done. And so you could have an encoder that spun more times in the motor and still back out the position. You could also have an encoder that, well, you could have an encoder that spun fewer times in the motor, but I don't know if you want to even talk about that option. But you could have an option where the encoder spins a lot more. And that is what you've got on the integrated encoder for the Azimuth motor. So it spins multiple times for one rotation of the module angle. The challenge with this is that that number of rotation counts has to be stored somewhere. Some computer somewhere has to remember that value. And so if, you know, I can't remember if it was in the last meeting or maybe the meeting before, we talked about the difference between volatile memory like in RAM and non-volatile memory on your hard drive as a file. That piece of information is always going to get stored in volatile memory. So if you lose power to that computer, you lose memory of what step you're on and what rotation you're on. And effectively, you now forget what direction your wheel is pointing. So even though you've got that encoder, you now no longer know exactly which direction the wheel is pointing. This would be a very serious problem in a match. So Mars had this exact problem last year with their Swerve drive, where under various situations, they would draw enough current on their motors that they would turn off the speed controller. They were using Talons for their Azimuth motor, and they were remembering that value on their Talon, not on the RoboRio. And so when the Talon would turn off and then turn back on again, they would have no idea which direction all four of their wheels were pointing. When your wheels aren't aligned in the Swerve drive, it's basically impossible to drive. It becomes impossible to control that robot. And so there were many matches that they were in where they'll get, you know, a couple of seconds into the match, they'll lose power for a second, the robot will come right back up, but they'll be out for the rest of the match because their wheels will be pointed in the wrong directions. So that was one problem that we wanted to avoid. The other advantage that we have by using this extra encoder is the integrated encoder here is just a counter. So it counts pulses of light or magnetic pulses. I'm not sure which one it is. I would have to go back and look at the documentation from the Neo. I'm pretty sure that it is, actually I think it's magnetic pulses. Anyways, it counts pulses of some signal as the motor rotates. That means that when you turn off your robot at the end of the match and you turn the robot back on again, that counter is reset. And so you would have to start each match with all the wheels facing forward and ready to go so that when you run your code, the wheels are properly aligned. That's not ideal. That's sort of one more thing that the drive team has to worry about, and it's something that has to be very precise. And so you don't really want the drive team to have to align each wheel perfectly before each match starts. So the extra encoder that we have on the Azimuth motor is an analog device. It is similar to a potentiometer, although Tag was saying that it is actually it's actually technically what's called a Hall effect sensor inside of the little box. Hall effect sensors also use magnets. I have to go back and look at the spec sheet to see exactly how that one operates. Whether it's a Hall effect sensor or what's called a potentiometer, the functionality of the sensor is identical. Basically, depending on the angle that the encoder is set to, the electrical resistance from one end of the sensor to the other end of the sensor changes. So your resistance is very low at, say, 0 degrees and very high at 360 degrees. And when you go back to 0 degrees, you now also have a low electrical resistance. The way that we use that is we apply a voltage, in this case 5 volts, across the sensor. We literally hook up 5 volts to one end, and then we read the amount of voltage on the other end. And the higher the resistance, the lower the output voltage is going to be. So at one position, the encoder might read 5 volts, and another position, it probably only reads 1 volt. And at angles in between that, it reads, say, 3 volts or 4 volts. So by reading the voltage on the other end with one of the analog ports on the RoboRio, you can identify the angular position of the sensor. The really nice thing about that is if you turn off the robot and turn it back on again, the value that you read from that sensor is the same. Because it is physically has a different resistance, it doesn't need memory. So no matter how many times you cycle the power of the robot, you're always going to be able to boot up and immediately know the true position of the wheels. As a result, the drivers do not have to reset the wheel locations before each match. They can put it down theoretically in whatever orientation they want, and the robot will figure things out from there because it will read the correct value. Any questions on the difference between those two encoders or the two different motors that we've got? Okay, so Ethan, I see you hanging out on here. What is the disadvantage of using these types of encoders? And what did we do to fix it?
I don't remember, Luke.
Okay. Amelia wired them, or wired the first one. Does Amelia remember?
No, I don't.
It's okay. It was December.
I do remember, actually.
What do you say, Ethan?
Isn't it with interference?
It is with interference.
The aluminum foil.
Mm-hmm. Alex, do you want to talk about that at all?
Okay, so there's like something to do with like how direct DIO something. Those ones are either 0 or 5 volts, but when the analog ones, if they like touch stuff, they mess up, and it's 0. Like it's not or, it's like everything in between. So like if it brushes up against stuff, it like doesn't have a happy time.
Yeah, that's exactly right. So let me draw that for you guys. So, and maybe this is also saying, you know, we can also talk about if we want to talk about some electrical subjects too. We can set up some sessions on electronics and pneumatics. So I'll just give a brief intro here. So if we have this little plot, and on this axis we have voltage. This is sensor voltage. And on this axis we have time. So it's just how the sensor voltage changes with time. And let me draw, we've got, let's see, we've got 0 volts, and then up here we've got 5 volts. Got 5 volts. Let's see here. I'll do that. So there are essentially two types of sensors that we're using. One of them is called a digital sensor, and one of them is called an analog sensor. So digital sensors or digital signals in general, are typically considered to be more modern. And they're what allows us to have very high data transmission rates between devices. That's how we're able to send lots of data. And the way they function is they are either off or they are on. So you would have a period of time where it's off, and then it would go straight to 0 to 5 volts for some period of time, then go down, and then maybe you'd have some pattern of pulses from 0 to 5 volts, okay? And the information that you care about is stored in the pattern of pulses that you have. So it would, one of the terms is you would encode the information that you care about in these pulses of information. And so that is digital. Okay. See if I can change that color. The other option is an analog sensor, which uses an analog signal. And those values, or those sensors, store their information as the actual voltage. So the value being output by the sensor at any given time is its actual voltage. So here 0 volts means something, 2 volts means something, 4 volts means something, 5 volts means something else. Okay, so that is analog. Okay. There we go. Okay. Now, the other reality is these data get sent on wires, physical wires on the robot. And we probably should talk about this in a different session in more detail, but as electricity moves through a wire, it generates a magnetic field. The inverse of that is also true. If there is a magnetic field that is changing, it generates electricity inside of a wire. This is the fundamental principle for how motors work. You generate electricity in a motor, you put electricity in a motor, you get a magnetic field that oscillates. And then if you spin it backwards, like with your hand, you will have a moving magnetic field that generates electricity. And now your motor is a generator instead of a motor. So that's why the robot can turn on when you push the robot really fast. The downside is that's really great. That's how all of electrical generation works for the world. The problem with that is we have lots of things on the robot and other robots near us that generate magnetic fields, particularly the motors. Right? The whole point of the motor is that we're generating moving magnetic fields. And those magnetic fields are inducing electrical currents in our wires, including our sensor wires. And so instead of having really clean signals like this, what you really have is some amount of noise always sitting on top of your data lines. And as you spin up the shooter, or as you move the wheels or do anything like that, that noise profile changes and can be better or worse. In a digital signal, this isn't so bad, because as long as this value stays kind of close to 0, and this value stays kind of close to 5 volts, you still know that this is off and this is on, and you can still count your pulses and you still receive your data cleanly. In an analog sensor, though, any noise that is on that data line actually changes the value of the data. It actually changes the value that's being reported to the computer. And so as things happen on the robot, the position that's being reported by the analog sensor is going to change even when the real position of that sensor is not changing. And that's going to make the Swerve drive difficult to control because it doesn't have a reliable measurement. One of the ways that you can fix this is, there's a number of ways. One of the ways you can fix this is with shielding the wire. Basically, you put another piece of metal around your wire so that magnetic fields induce electric current in that piece of metal and don't penetrate to the metal in the signal wire. There are very fancy ways to do shielding, which work great. We did a really simple one, which we just took some aluminum foil and wrapped the wires. At some point, because it is an amount of weight, we should look to see if we need that or not. We didn't have enough time to independently test the Swerve drive both with and without the aluminum foil to see if it was making a big enough difference to improve things. We just went ahead and did it because we were running out of time and we knew this could be a problem. In the future, we should look at a test case of no aluminum foil, and then professional grade shielding and see if we get any improvements, if there's a worthwhile improvement between the professional grade shielding and the aluminum foil, or if we don't need shielding at all. So we should at some point look at all those scenarios so we understand what the best approach is. Are there any questions about the encoders or analog signals versus digital signals? Okay. So let's see. The last thing to mention here is, one second, is the other sensor that we need to control the robot. So with a Swerve drive. And so the other one that we've got here is we need an inertial measurement unit, or an IMU. An inertial measurement unit basically measures angles. And so this allows us to know the robot's angle with respect to the field at any given time. We'll talk about it later on, the difference between controlling the robot in robot-centric versus field-centric. But the gist is, in field-centric mode, pressing forward on the joystick always moves the robot forward down the field. Pressing left always moves it left, and pressing right always moves it right. This is a much more intuitive, or a much easier way to control a Swerve drive than other methods, but it requires us to have a measurement of the robot's angle at any given point in time. And for that, we need the IMU. And we'll talk some about the limitations of an IMU as we get to that point in the workshops. Are there any other questions about the sensing or any of the hardware associated with the Swerve drive before I go on to some of the code stuff? Okay. So what I'll do, because I don't want to start the Swerve math with only 15 minutes left, I'll just show you where the Swerve is in the code and talk about the PID, do a little bit of review on the PID algorithm. And if we have time, I'll talk about sensor calibration. If not, we'll leave that for a different time. So let me go ahead and open up robot project. So control for the drive motors on the Swerve drive is pretty straightforward. Each wheel has a power that's going to be determined by the math that we'll work out later, and it's getting sent directly to each one of the drive wheels. There are advantages to doing a more complicated approach where instead of applying a certain amount of power, so the next advanced thing would be, instead of applying a certain amount of power, apply a certain amount of power that is scaled by the battery voltage. That way, as your battery drops, the motors respond in a more consistent way, or to how they were with the higher battery voltage. The advantage of this that's not really important for a non-Swerve robot. For a Swerve robot, that is a bit important because you are merging instructions about how the robot should translate with how the robot should rotate, and that's what we're going to talk about. And the merging of that information relies on power being directly related to wheel speed. And that is not strictly true. And so as the battery changes, the behavior of the merging between the robot's rotation and the robot's translation will behave differently. The even better solution is that instead of applying a certain amount of power, you apply a target speed and have a PID and a feed-forward controller that maintains the wheel velocity so that you're setting a goal velocity, because what we'll find is that the math that we're going to work out today or next lecture is not really giving a goal power. It's giving a goal velocity. And when you give it a goal power, when we're giving it a goal power, it is assuming that, you know, if you increase the power by 50%, you've also increased the wheel speed by 50%, and that's not actually true. The wheel speed and the power that's being applied to that wheel is not a linear relationship. So that would improve the wheel performance. We are not doing either of those two methods, so we're still using the most simple method for controlling the wheel speed on the Swerve drive right now, which is direct power application. So right now the code's pretty simple for that, but as we look in the future for improving the reliability and the controllability of the Swerve drive, we can talk about some more advanced speed control algorithms. Control of the azimuth angle, the azimuth motor, is a little bit more advanced. We do need to use a PID controller to control the azimuth angle. And so our inputs are for right now, treated as a angular distance that you have to travel. So instead of giving the PID, saying that the PID has to go to position 30 degrees or position 180 degrees, we're instead saying that the wheel currently has to spin positive 30 degrees or negative 180 degrees in order to get to its goal. And so if you look at the PID block here, we've done something a little bit unconventional, and we're not quite using this properly. We can talk in more detail later about why it is still working, but our goal is actually always 0, and our process variable here is this angular distance. So the PID is trying to drive the angular distance between its current position and the real goal to being 0, which is the goal of the PID algorithm. So instead of putting in the angular position goal, the real goal, it says, in other words, let me explain it this way. Let me draw it out. Maybe that will help. So if you've got your coordinate system here, and the robot angle is currently at, we'll call that 20 degrees, because again, this is at 0 degrees there. And where we're trying to point the azimuth module is down here at 100 and, so we said that was 20. We're trying to point it at, we'll call it 160 degrees. Instead of putting 160 degrees into the PID block as the goal, instead we'll do the distance between 20 degrees and 160 degrees, which would be 160 minus 20, which would be 140 degrees. So it's saying that the current error is the robot has to move its wheel 140 degrees in the positive direction in order to get from where it is at currently to its goal location. Does anyone have any guesses or remember why we can't just put 160 degrees into the goal and put the encoder value into the process variable, why we have to do this angular distance portion for it?
Because angles wrap around, so we might have So the angle values that seem far apart because they're close together in the circle are not?
Yep, yeah, exactly. So, if you calculate, if our goal angle was that one instead, so it's 340 degrees, the angular distance between 340 and 20, like the robot should move the wheel from 20 to 340 in this direction. But if you were to do 340 minus 20, you would get a much larger number, right? You'd end up with 320 degrees of travel. And so the wheel would actually spin in the wrong direction for longer than it needs to. And the PID algorithm code just does a simple subtraction. So it just subtracts the goal from the process variable. It doesn't handle angles well. And so we have to have a separate block that does handle all of the oddities with working with angles where the angle wraps around from 0 to 360, where 180 and negative 180 are actually or 180, sorry, 0 and 360 are actually the same angle, where you might have angles in as 180, or you could also measure this from like 0 to 180 and 0 to negative 180. So you have a lot of different sort of options for how you define the angle. And so we do have to do that math before we get to the PID. And that's one of the other things that we'll talk about is how that math actually works. But for right now, that math is done beforehand and put into the PID. Does anyone have any questions, not necessarily with how we're going to solve that, but just with the concept of why that's a problem for calculating the values that we need for the PID controller? Okay. And then the last question we have on the PID is, let's see, oops. If we look at the values here, you'll see that we have a KP of 0.005, and then we have zeros for KI and KD. Can anyone remember why for the Swerve drive we aren't using either the integral or the derivative term?
That's because we have a lot of internal friction, so it does kind of act as the derivative, and we don't need to code that in.
Yep, correct. So we've already got real friction that's doing the damping physically in our system, so we've been able to get away without a D term. And then the reason we don't have an integral is, the motor actually does a very good job of getting the wheel to the correct position. The inertia of that wheel, the mass of that wheel, is fairly small relative to other things that we control, like an elevator. And so your steady state error tends to be pretty low. The other challenge with tacking on an integral component to this is because our goal is always changing, the driver's always moving to different locations, most likely the integral would never really come into play because we'd be constantly resetting, or the integral would no longer be meaningful because the accumulated memory of the error isn't really accurate because our goal is constantly changing. So we would end up with a lot of lag in how we remember the steady state error as the driver tries